Hi, my name is Adam, and I'll be covering the electrophilic aromatic substitution reaction in this video. So, to start, the electrophilic aromatic substitution reaction is a really important reaction in organic chemistry, which allows you to take an aromatic compound, say like benzene, and add in a substituent. So generally, for all reactions of this type, we're going to start with an aromatic compound, in this example here, benzene, and an electrophile. This is usually like a usually a positive ion, something that's going to be electron poor. Because of that, the electrons on this benzene ring, which has a lot of them, are going to attack the electrophile and form a bond, sort of like this. And since aromatic rings are stable, it does not want to stay like this. So it's gonna try to kick off one of the atoms here. And in the forward way of this reaction, it's just gonna take the electrons from that bond with the hydrogen and put them back into the ring, giving us our product. This can be done with a whole bunch of electrophiles. So one of the most simple ones are bromine and chlorine. So normally with ions, bromine and chlorine are going to be their bromide and chloride, the negative ions. However, for this reaction, we're going to need an electrophile, something positive, electron poor. So we're going to need the positive ions of these, which can be obtained with a catalyst, a Lewis acid. Usually that's going to be iron bromide or aluminum bromide, in the case of bromide. For chloride, that would just be chlorine there instead of bromine. So how this works is we have the elemental form, the bromine, the two bromines bonded to each other, and the Lewis acid catalyst. So the electrons from one of the bromine are going to attack the metal ion, the metal part of that molecule, and give us this intermediate. And then from here, the electrons in this bromine-bromine bond are going to move over here, giving us the Br plus and FeBr4 minus. This is what we care about. And see from here, it's the positive ion, that's what we need. So it's basically just gonna work exactly like this, going from this to this. And reminder, this also works with chlorine, just instead of bromine and all of these, it's just going to be chlorine. So a different electrophile that you can use is for nitrations, which uses this. So to get this, you're going to need, the starting point is nitric acid, HONO. No, that's not right. HNO3, which looks a little like this. So to get this from this, one way we can do that is take off this over here. And a way to do that is with an even stronger acid, sulfuric acid. So if we go over here, we have HONO. And we have that. So the electrons of this oxygen over here are going to go over here, and over there, which gives us HOH plus NO. And this over here is a pretty good leaving group. So the electrons from this oxygen are going to go there. The bond electrons are going to go there. And now we have just water and our electrophile. And again, it's gonna work like before, where have our starting material, got our HNO3, H2SO4, and there we got our electrophile. Back to here, it's going to go through this, and that gives us our product. Hi, future me here. There's something that I forgot. It was sulfonation. It's very similar to the nitration reaction. So basically, how in nitration, it used a sulfuric acid to kick off water from a nitric acid. This is going to do the same thing, but to a sulfuric acid molecule. So we got one sulfuric acid, we got a second molecule of acid. It doesn't have to be sulfuric acid for the one that's doing the protonating, it just has to be equal or stronger. So the electrons from here are going to go over to there and steal that hydrogen. Electrons are going to go to there and move on to this step. Just like earlier. And then it's going to, the bond is going to kick off that water molecule. So now we get this, which can go react with, say, a benzene to form this. So those were just some of the simpler electrophiles, but this can also be done with, like, say, carbon, to make carbon-carbon bonds, which are really important in organic chemistry. So the way this is done is through Friedel-Crafts acylation. Which basically is, like here with the bromine, we have the, it's not going to be Fe, it's going to be AlBr3, our Lewis acid catalyst, and we also have something with the halogen on it, so it's just going to be, say, bromine and whatever carbon chain group you want, so like that isopropyl, that's gonna add on, or say like, it can be whatever you want. So it works very similarly to what I showed before, where got the bromine, the catalyst, the electrons here go after that, positive ion, and got your electrophile. So keep in mind, since it is a carbocation, it will undergo rearrangements. So say if you wanted this molecule, isobutyl benzene, it's not quite as simple as that, because if you, say, use this as your as your reagent, you're effectively going to be making this, which, no, not that. You're going to be making this, which will undergo rearrangements. The hydride here is going to shift and give you this. So if you just do this Friedel-Crafts acylation, Friedel-Crafts alkylation with this, you are not going to get that. You are going to get this. To get around that, one thing you could do is something else I briefly misspoke about, the Friedel-Crafts acylation. This one over here is so mainly the difference is instead of an alkyl group attached, it's going to be an acyl, which is going to look like it's going to look something like, say, this. So basically, same procedure as before. Got the starting material. The electron's gonna do its thing. And here you have your electrophile, which is gonna do some resonance thing to turn into this. So from here, just like before, it's gonna go that plus your this to form that. And since it's just basically an acyl group, a carbonyl, you can convert that back to an alkyl through the Clemmensen reduction, which is zinc amalgam and an acid, or the the Wolff-Kishner reaction. I'm not sure if I spelled that right, but it's close enough. Which is hydrazine, 2H4, and a basic environment. One thing to note about the Friedel-Crafts acylation and alkylation is that in order to do that, it has to be more reactive than more reactive or equal to benzene. Hi, future me again. One thing I forgot to mention about the Friedel-Crafts alkylation is that it only works for alkyl groups, like that or that. It does not work for anything else. Say, if you had something like this with a double bond there, it doesn't work. Oh, what I mean to say is it needs to be a sp3 carbon right there. It can't be like a double bond with this molecule, or a can't be like a double bond or like a aromatic ring. It has to be like sp3. Whatever after that doesn't really matter. Probably could put one there or something, but for like right next up to the bromine, it has to be sp3. So that brings us into our next part with activating and deactivating groups. So some substituents are activating, meaning they essentially donate electron density. So those are going to be, that's not right, like your anything with carbon right there, anything with oxygen right there, like phenol or any sort of something like that. I think that one's called anisole. Or any sort of thing with nitrogen there, like amines, or what's it called? Aniline, which has 3 hydrogens on there. Those are going to be your activating. Meanwhile, for deactivating, it's going to be things that are like stealing electron density. So you got your halogens, your anything with a carbonyl right there, or basically anything with a double bond there. So your nitro groups are going to also do that. So these are deactivating. So these things are going to make it more prone to reaction, so where you can use Friedel-Crafts, and these are going to make it less not as activated, so you cannot use Friedel-Crafts there. One interesting thing to know here is this is also mostly what determines when there's more than one substitution that you're doing, and where the placements of those groups are going to be. So as you may or may not know, there's ortho, which is right next to each other. Para, which is across the ring. And meta, which is in this 1-3 position. So your activating groups, all of these up here, are going to orient them towards ortho or para. So if you say have toluene and do a, say, bromination on it, it's either going to be here or here. It will not be that. It will not be meta. However, and these deactivating groups, these ones over here, oh, not that, I'll come back to that. These two will go towards meta substitution. So you have a nitro group here, and you add another one, it's going to go to the meta position. Because of this, the order you add substituents on is pretty important. So let's say we want to add 2 groups onto, say, benzene. We want, oh, sorry, I forgot to mention something. So halogens, like bromine, chlorine, that right there, those, while being deactivating groups, act similarly to activating groups when it comes to substituent placement. So it's going to be going to ortho or para. So say we're adding a nitro group, and a bromine to some starting material, say benzene. So based on what we do first, if we do the nitration first, that placement really doesn't matter because it's all the same all around. And then from here, we do our bromination. Since it's one of our deactivating groups, that's gonna orient us to meta. It's going to give us something like this. However, if we do the bromination first, get our bromine on there, and then do our nitration, since it's, well, it's deactivating, but since it's the exception to this, and we'll go towards ortho or para, our product will either be, our product will be this one, the ortho product, or this one, the para product. I say will be and not or, because when reacting this in chemistry, it's going to be in like a decent quantity, and like all the things in a mole, some of them are going to be doing this, some are doing that. They are not going to be doing this. Okay, let's see, final things I've missed. Aniline, you can make that a substituent. I mentioned it earlier, the NH3. To get that, you just need a nitro group and do catalyzed hydrogenation. So H2 and some sort of catalyst, nickel, palladium, platinum. I'm just going to put nickel. And that reduces the nitrogen up here to this, NH3. And as I said before, that is going to be one of our activating groups. And and one final thing, the Friedel-Crafts acylation and alkylation, these are not the only ways to add a carbon-carbon bond to one of these. You can also use, say, like, Grignard reagent. So, say you have bromobenzene, react it with, sorry about that. So you can react it with magnesium to get a Grignard reagent. And use it like any other with, say, you wanted to create our thing over here. Wait, no, that might not work. Let's say you wanted to do it on, say, this. It's going to act just as it would normally. Right, nope. It's gonna sp2 reaction, I think, if I remember correctly. And give us this. And then one final way the book says how to do is you can so the textbook says you can also use acids. So it has this example. I think phenol will just work. We have an alkene and a alcohol in acid. And right, nope. Scratch the alcohol. Since this is going to be this is just for that for now. It's going to be from this to essentially a carbocation. It just works like before. And then with this, it's just going to add on like this. Okay, so that seems to be it, and forgive my rambling over the course of all this, and good luck on your class on this, and I hope it'll be useful.